Hello मेरे प्यारे बच्चों, welcome back. I know, your exams are just around the corner, but don't you worry one bit. Today, we're gonna crack one of the most important chapters, structure of the atom. And you know what? We're gonna do it like a detective story. We're on a mission to find out what's hiding inside, well, everything. So are you ready? Let's dive in.
First things first, just look at your hand. Now look at the phone you're watching this on. What is all this stuff made of? I mean, if we could zoom in and keep zooming in, what's the smallest possible thing we would find? That is the big mystery we're going to solve today.
So, our story starts with our very first suspect, an idea from a scientist named John Dalton. He said that everything, you, me, this screen, it's all made of these tiny, unbreakable balls called atoms. Just imagine the smallest possible molecule, one that you absolutely cannot break any further. That was his idea of an atom, just a solid, tiny little ball.
Now, Dalton's idea was a fantastic start, but it had one tiny problem. It couldn't explain something you've all done for fun. You know, when you rub a balloon on your dry hair, and poof, your hair starts standing up. That simple little party trick was actually a huge clue that the atom was not just a simple solid ball. There had to be something smaller, something with a charge hiding inside. The case was just getting interesting.
And pretty soon, the detectives, the scientists, they found their first big clue. They discovered a teeny-tiny negatively charged particle that was hiding inside every single atom. This, Bachon, was a massive breakthrough.
So how did they find it? They used this cool piece of equipment called a cathode ray tube. Basically, they took a glass tube with most of the air pumped out and passed a really high voltage current through it. And when they did, they saw this mysterious green beam traveling from the negative side, the cathode, to the positive side. This beam was the first ever proof of those tiny particles we now call electrons.
And these so-called cathode rays were pretty special. They found out they travel in straight lines, and they could be bent by magnets, which proved they had a negative charge. But here's the most important part. It didn't matter what gas they put in the tube or what metal the ends were made of, they always got the exact same particles. This was huge. It meant that these electrons are a basic ingredient of everything in the universe.
Okay, so now we have a new clue, this negative electron. So a scientist named J.J. Thomson decided to draw the first picture, like a police sketch, of what this atom might look like. He had to figure out how to fit these negative little guys into a neutral atom. And he came up with a very tasty idea.
He said, what if the atom is like a watermelon? The whole red, fleshy part is a big ball of positive charge, and the black seeds are the tiny negative electrons stuck inside it. Or, a much better example for us, it's like a motichur laddu. The whole sweet bundi part is the positive charge, and the little bits of elaichi or pista are the electrons scattered around. It made sense, right? It explained why the atom was neutral overall. But, was it correct? Let's find out.
All right, quick pause in our story for a very, very important exam question. You see this kind of notation all the time in your textbook, right? An X with two numbers. But how do we write it, and what do those numbers actually mean? Take a second and think about it. And here's the answer. The X is the element symbol. The number at the bottom, Z, is the atomic number, and that's just the number of protons. Easy. The number at the top, A, is the mass number. Here's a trick to remember. A is for all together, meaning protons plus neutrons. So Z is just protons, and A is all of them together. Got it? Simple?
Okay, let's get back to our investigation. And trust me, this is where the story gets a massive, absolutely shocking twist. Another scientist, Ernest Rutherford, he decided to put Thomson's Lotto model to the test. And what he found, oh boy, it changed everything.
So here was his plan. He took a sheet of gold foil that was unbelievably thin. We're talking just a few atoms thick. Then he fired tiny, positively charged bullets called alpha particles right at it. Now think about it. If the atom is like a soft laddu, what should happen? The bullet should just pass straight through, right? Maybe a few would get slightly pushed aside. That's what he expected.
But what he actually saw was completely nuts. It was so unbelievable that Rutherford himself said it was as if you fired a 15-inch cannonball at a piece of tissue paper and it came back and hit you. Can you imagine the shock?
So what exactly did he see? Well, first, most of the particles did go straight through, just as expected. Okay. Second, a small number of them were deflected by small angles. Interesting. But third,
And this is the part that blew everyone's minds. A very, very tiny number, like maybe 1 in 20,000, hit the foil and bounced straight back. Bounced back! How is that even possible from a soft lotto?
This shocking result could only mean one thing. The LATO model was wrong, totally wrong. Rutherford realized that the positive charge in almost all the mass wasn't spread out at all. It was concentrated in a super tiny, super dense spot in the center, which he called the nucleus. And the rest of the atom? It was almost entirely empty space. That's why most particles just passed right through. The only ones that bounced back were the unlucky few that scored a direct hit on that tiny, heavy nucleus. But wait, Rutherford's amazing new model created a new, huge problem. We all know that opposites attract, right? A positive nucleus and negative electrons, they should be pulling on each other. So why didn't the little negative electrons just spiral down faster and faster and crash into the positive nucleus? Boom. The atom should collapse in less than a second. But, well, we're all here, aren't we? Our atoms are not collapsing. So what was going on?
So the atom is in trouble and it needs a hero. And that hero was the next great detective on the case, Niels Bohr. He looked at all the clues, the fact that atoms are stable, the weird patterns of light they give off, and he came up with a brilliant idea that saved the atom from total collapse.
Bohr's big idea was this: electrons can't just be anywhere they want. No, they have to be in certain, special, fixed orbits, or what we call energy levels. Think of it like lanes on a running track. You can run in lane 1 or lane 2, but you can't run in between the lanes. It's the same for electrons. Because they are stuck in these special orbits, they don't lose energy, they don't spiral in, and the atom remains stable. Problem solved!
And you know what's really cool? Bohr's model also explained another mystery. When you heat up an element, it glows and gives off light of very specific colors. It's because the electrons get excited and jump to a higher energy level. But they can't stay there forever, so when they fall back down, they release that extra energy as a little packet of light of a very specific color. Every jump gives a different color. That's why every element has its own unique color signature. It's like its own atomic fingerprint or its own special Instagram filter.
Fantastic! So we've gone from a simple ladoo to a tiny solar system, and we've finally solved the basic mystery of the atom. Now let's switch gears and do a super quick revision to make sure you're all set for your exams. Ready? Let's go.
All right, here is a classic exam question, straight from your textbook. Take a look at this symbol for bromine. You have to find the number of protons, neutrons, and electrons. I'll give you a moment to try it yourself. Go on.
Okay, did you get it? Let's check. The bottom number, Z, is 35. So number of protons is 35. And since the atom is neutral, the number of electrons is also 35. The top number, A, is 80. So to find the neutrons, we just do A minus Z. That's 80 minus 35, which equals 45. So 45 neutrons. See? Easy peasy, lemon squeezy.
And finally, Bacho, here is the ultimate cheat sheet. This little table has everything you need to remember about our 3 star players: the electron, the proton, and the neutron. Their charge, their mass, everything is right here. Go on, take a screenshot of this right now. I promise it will be super, super helpful for your last-minute revision.
And I'll leave you with one final question to think about. If Rutherford was right, and you, me, the chair you're sitting on, if everything is 99.9% empty space, then why does it feel solid? Why can't I just push my hand straight through this table? The answer has to do with the powerful forces between all those electrons. Something to chew on. And with that thought, that's all for today, Bachon. Study hard. You are going to be brilliant. All the very best.